Arya will be speaking soon, and Mangesh. They're giving us a platform as young individuals to express at the same level as someone who is an open source legend like Covid. So this is a huge thing for me, and I'm incredibly grateful to them. Now, let's begin with the famous discussion: Windows or Linux. Then, if you pick Linux, you have which distro do you pick. Beyond that, you have which DE do you use GNOME, do you use KDE. These are all discussions that we've all seen or even had as open source members. But have you really thought about like MacBooks? I'll begin my talk with talking about Apple, controversially even. So you might have thought to yourself, can I actually develop on a Mac? Like half of the speakers had MacBooks if you saw. So why is this? Why did they have so much success in the developing community? So this success can be attributed to a certain amount of things. Before we get into that, I will come back to my topic actually. So we're talking about RISC-V. Oh, one second. Yeah. Okay. Yeah. Cool. All right. So RISC, the first part of RISC-V. So RISC stands for Reduced Instruction Set Computing. When computer architecture was a very rapidly evolving field, so we had this philosophy of RISC versus CISC. CISC is just complex. As you can see from the graphic, RISC puts the load and all of the complexity on the compiler compared to the processor, which is common in CISC. So as you might know, Intel and AMD, they use x86, right? So those are CISC. And now Apple came in and they decided that they wanted to make iPhones. Then they decided they wanted to make their own chips. So we had iPhones with ARM chips. ARM is RISC based, right? So then they competed with Qualcomm. They were outperforming Qualcomm at a very large scale, even in games. And eventually they got tired of Intel. If you remember like late 2010s MacBooks, they were horrible. They had overheating issues and everything. So they just made an iPad, they added a keyboard, and you can see the results. Those are M1 MacBooks we see today. So this example, I feel like it highlights how important microarchitecture is. And in today's day and age, microarchitecture is such a complicated topic that most people don't even have a grasp for it, and you don't need to, because you just deploy your web app and you're good. So now RISC-V. RISC-V, as you can see in the logo, it's a new instruction set that's been designed by RISC-V International. So RISC-V refers to multiple things. You can see the ISA. So every microarchitecture has an instruction set that they have to follow. Now, if we compare RISC and CISC to, let's say, languages, I would say RISC is more like English, whereas CISC is more like Japanese. So in Japanese, you have very complex characters which allow you to express a lot of things very quickly. In English, you can express the same amount of things with more syllables, since there are only 26. But that also makes your life easier when you're learning it, right? So that's the ISA part. So each architecture has its own ISA. Then we have the association. So where's the open source in this, you might ask? So RISC-V Association is a non-profit headquartered in Switzerland. This is intentional for avoiding geopolitical issues, and their whole intention is to preserve the IP and allow anyone and everyone to utilize RISC-V, since the entire ISA itself is open source. And then the third thing, RISC-V products. So recently there was a laptop launched with RISC-V called Roma. Other than that, there are SBCs, so stuff like Raspberry Pis, they are being shipped with RISC-V. Now, these are the associated organizations which are putting money into RISC-V. This is important because, as Covid said, if you want to work in FOSS, you need money. The same is true for hardware to a larger extent. So in hardware, the development cycles are in years, in decades, and you need money in millions compared to thousands of dollars. You're not just trying to feed yourself if you're developing open hardware, you're trying to build a company probably. So as you can see over here, we have the Indian government. So MeitY was one of the founding members of RISC-V International. Now why RISC-V? Open source. We all know the benefits of open source. It allows for privacy, it allows for better security, blah blah blah. Another thing is, open source allows for continuous issue triaging. So in open source, it's a developmental process. You don't release a stable version and call it a day. If you've ever tried to use Windows updates, they're annoying, they break. But has Windows fixed it? No. In open source, if there's an issue with a kernel update, someone will try to push a commit which will fix it. This continuous improvement is also essential for chips that we design because of flaws such as meltdown and Spectre. So I won't get into the details of the meltdown and Spectre, but essentially there was a way for people who don't have the privilege to access content on your device by running malicious code. Efficiency improvement. So Sci-Fi, which is one of the major startups in this field, they recently announced that their chips can compete with ARM chips with 42% less area. So that means 42% less cost to produce the device. This is extremely important since most of the costs of devices can be attributed to licensing costs and the cost of production in today's game, especially in the mobile domain. So performance improvements, I'll show some statistics later on, and extensibility. So as people who use open source, who contribute to open source, our main thing is we like to hack open source. We like to improve it and modify it, tailor it to our wants and needs. This is what RISC-V provides. So personally, my work at ISC involves developing a RISC-V coprocessor. This is very simple to do compared to something like x86. I'll get into the details later. But even Apple, if you buy an iPhone right now, it has a RISC-V chip in it. It's not the processor, it's a coprocessor. And of course, RISC-V came out of an academic project, so it has excellent documentation. So yeah, these are the benchmarks that show, this is from 2021 as far as I remember. This shows that RISC-V is at least on par with the current other architectures, in spite of being open source. So there's also this corporate belief that open source inherently is less secure or that it's not maintained as well or it's not performant. Just believe that it's inferior. This is not true, as you can see from these benchmarks. So CodeMark is a very simple silicon level benchmark that you can run in order to analyze how well a chip is running. So how do you get started with RISC-V then? So I talked about how you need millions of dollars to get started with open hardware. This is not true nowadays because emulation is a thing. So single board computers, so you will obviously have heard of Raspberry Pis. These are very common in the open source community. If you want a RISC-V based board which just allows you to tinker around, it's gonna be costly, especially in India with all of the import charges. If you try to upload a RISC-V code, so that lets you run your code on some generic device. That's called an FPGA. I won't get into those details, but FPGAs are essentially like a blank board that you can program with whatever you want. You can do this again, but it's going to be similarly costly. Emulation is free. Nobody is stopping you from downloading from open source. So the way that I want to explain how you can easily get started, it involves QEMU. And for this is the architecture on this side, and this is the QR code. So if you want instructions on how to get started, you can just scan this QR code. And yeah, so essentially you have a normal laptop, let's say x86. On that you want to run RISC-V code, right? So there was initially a way to run directly with this code. But if you want to run an entire Linux kernel, because that allows you to use all of the bin utils, right? So you can just do that nowadays. So there's this thing called the Debian image baker. So this is the official Debian member who has released this. He just ships Debian SID images. So what you do is you emulate that image by emulating the RISC-V core, and then you run the Debian image on that. So this gives you GCC, it gives you Debian recalls, you can do whatever you want, and you can have the latest kernel running. And once you've done this, you have SSH into that, and you can try and deploy whatever you want. Why is this important, you might ask? So as software developers or students, for software developers, it's important to keep track of industry trends to adapt your code for new architectures. Google recently announced that they're going to support RISC-V as a Class A architecture for Android. This is just one example of how RISC-V will, in the next 10 years, become extremely relevant, even for software. So if you just get started with it right now, it's going to help you quickly transition even your open source software to RISC-V. For students, it's an emerging technology, just the way people keep talking about AI non-stop. RISC-V is a thing you should be aware of, and this is a very easy way to get started with it. All you need is a normal computer running Linux. So yeah, this is what it will look like, and I would have gone into the details on how you install it, but it's on the GitHub repo. So I have this demo running right now in another window, and we'll be working on that. Now, how does it work? How does Hello World work? Before this, I'll just show you the demo working right now. So as you can see on the left side, we have a Debian install. It's in a VM, but this Debian install is based on x86. As you can see, this is the chip it's running on. On the right side, if you see, I'm using QEMU and I have RISC-V over here. So essentially, all of the stuff we saw in the previous slide, this entire shell is being run in this VMI app. Now, how do you get started with coding? You always start with Hello World, right? That's traditional. So how does Hello World work? You will probably know at least some of C, right? So in C, all you do is you assign a variable for Hello World, you store that variable in your memory, and then you print it. Right? Simple enough. Now when you go to assembly, assembly is a much more verbose way to write code. When you compile your code, it gets converted from C to assembly, and then you run that code, right? Once it's compiled. Over here, we have to set up registers and pointers. I'm sure you all love learning pointers in C in college. And you have to manually output each character. So that's one way you can use assembly to print Hello World. Something as simple as this, you already have a for loop. So now, Hello World, how do you print Hello World? So this is the RISC-V instruction set. This is the ISA I talked about. This is the 32-bit one. And as you can see, there are a bunch of instructions. So you might know XOR as a logic gate. You might know AND as a logic gate. Then there's a bunch of other stuff as well. So shift left, shift right, for example. There is an easy way to divide if you're using shift left, shift right. So these are all essential instructions that any device needs in order to function and compute, to be Turing complete. Now, these are very minimal compared to 500 plus instructions that you might see on a CISC processor. Now, let's write it together. Since the talks are a bit delayed, I won't be able to help you write it and demo it, but essentially I'll be explaining this. So this is a RISC-V program which will print Hello World. In this you have global start, you have start, and then you have print string. So you can think of print string as a function. Global start is just initiating the program, and start is your main, int main equivalent. In this, you're using RISC-V specific terminologies that again, if you want to get into the details of this, all of the documentation is easily available on RISC-V.org. So this code might look like gibberish, but I promise you, even if you ChatGPT it once, you'll get a really good explanation for this code. And even the comments I've mentioned, they're a good explanation. So as we saw before, there's a loop over here which prints every single character. And now we look at x86. x86, as I said, it's an exclusive agreement by Intel and AMD. So nobody else can make a x86 chip. And if we look at AVX, SVM, SMT, SJX, these acronyms might not make any sense to you, but all of these are like additions that they had to do to x86 in order to make it modern. So x86 was initially invented as like a patchwork ISA just to make the market work while Intel was developing their proper solution. And since it's so old, it had to add a lot of stuff. For example, AVX, that's for vector instruction. That's not included in core x86. So what this results in is 500 plus instructions in the modern instruction set. So imagine this code. This is a simple code, right? Imagine that you have to think about ADI, JL, LI, PQZ, and like 500 other instructions. You have to remember them, and that's how you write assembly. So as a young student, where have I seen assembly and people writing assembly in today's day and age? The most common place I've seen it is emulation. So if you're writing, let's say, a console emulator, you write it in assembly. That's the fastest way to write it. But with this current situation of 500 plus instructions, this doesn't make sense. So I would urge you to look into RISC-V, try to understand if it makes sense to you, and make the choice for yourself whether you want to invest in this ecosystem. But personally, giving you an anecdote, I wrote about RISC-V back in 2022, around the end. So it was 1 week before my JEE, and I decided I didn't want to study. Instead, I wrote like a white paper. I wouldn't call it a proper research paper. It was just a review of how the smartphone industry has evolved over the past decade. Now, I sent this review to over 300 professors all over the world because I saw this news. It said that Europe was investing like $160 million into RISC-V. They were just giving out money to whoever was building RISC-V ecosystems, compilers. They were building RISC-V cores. And I was like, this is the time where there is money in FOSS, in this FOSS software technology, as well as there's the potential and the government backing. All of these are extremely important. So I was like, let's do this. And that email is what got me that ISC internship. And that is how I was able to get into ISC a week before JEE. And I think it's a testament to how technology evolves quicker than academia. So you need to keep up as a student on your own and make your choices and keep learning about things that will take you forward in your career. Don't just do a Web3 course because somebody told you that it's cool. Don't just do blockchain because somebody told you. Think about it. Think why blockchain makes sense or doesn't, and then decide. Thank you.
Thanks a lot. We can take only one question. So.
I think this is a question relevant for pretty much anything related to RISC-V because I saw a discussion on GMP, the implementation of a lot of math stuff that's used in crypto. They mentioned that the beginner implementation takes like a really large number of instructions compared to other instruction sets, other ISAs, and I was wondering like. This is going to slow down crypto on RISC-V a lot, right? And we use crypto in pretty much, not the cryptocurrency, cryptography. We use crypto in pretty much any application, HTTPS, SSH, like anything that requires encryption, we use cryptography. So I was wondering, like, what does this really mean for RISC-V?
See, this goes back to like the slide I showed when we put it up. Yeah, this slide. So inherently in any RISC architecture, be it ARM or RISC-V, the effort is required on the compiler side. You can easily deploy simpler processors, and the compiler has to be more difficult. And right now I can show you this working Debian install. This is on RISC-V, right? So this is already functional and someone has done the work. I agree that compiler development and all of these renewables, basic things, they're more difficult on RISC-V. But it's already been done as a part of academia. Because RISC-V was developed at Berkeley, right? So they had the time to invest in it so that they could teach students how ISAs work, how chip design works in an easier manner. So they've done the work. Does that answer your question?
Not really, but in the interest of time, I will catch up with you later.
Alright, no issues.
Thanks a lot, Soham. Please give a round of applause for. I think it's good to try once in a while to move data from register A to B and doing some assembly. Can we? Okay, I thought we were doing everything.